Hello again, welcome to Basics of Finite Element Analysis Part 2. Today is the 4th day of the 7th week of this course. What we did in the last class, we solved a heat conduction problem as represented through Poisson's equation, and we had solved it for a square plate and the problem was symmetric in nature along 2 dimensions. What we will do today is something very similar, but we will extend that idea of symmetry further and we will see how we can exploit that other situation also. So, the problem we will solve is still the same, identically the same, which is that we have a plate where we are having heat conduction, u is 0 on all the 4 sides and the coordinate system is located at the center of the plate. The size of the plate is 2 by 2 and we have symmetry of geometry, symmetry of material properties, symmetry of boundary conditions and symmetry of the force term. And because of this we had said that the problem is symmetric along the x axis as well as the y axis. But there is one more plane along which it is symmetric, and what is that plane? So, the other plane of symmetry we will draw that separately just to make things clear. This is my original problem. These are my axes and we had said that the planes of symmetry, this is one plane of symmetry, this is another plane of symmetry, because along these 2 planes the geometry is symmetric, the boundary condition is symmetric, the force variable is symmetric and the material properties, they are symmetric, all those 4 parameters are symmetric. So, because of that we had broken this plate into the first quadrant and we just solved the problem for that. But as we look at this problem is also symmetric along a third axis, a third line, and that would be this line. Again, why is it symmetric? Along this line the geometry is symmetric, right? What about boundary conditions? On one edge, on this edge, on the vertical edge, boundary condition is del u over del n is 0 and on the horizontal edge del u over del n is 0, right. So, the boundary conditions are also symmetric. Geometry is symmetric. What about force? If I take along this line, if I take a point P1 and I take a point P2 which is a mirror image of this, are the material properties same? They are same. So, the material properties are symmetric. And finally, for the same 2 points, what is the value of F naught? At both those points, F naught is constant across the whole plate, and because it is constant, the value of F naught at point P1 and at point P2 it is same. So, it is symmetric also along this plane, right. So, I do not have to solve 1/4 of the problem, but I can even use 1/8 of the problem and solve it. So, in this case the complexity of the problem or the number of equations which I will have to eventually solve, it will go down by a factor of 8, not just 4. So, that is what we will do. So, we will draw this problem again. So, again my coordinate system, once I have identified planes of symmetry, it does not change. Okay. So, this is x axis, this is y axis, and I will draw my reduced problem So, the coordinate of this is 0, 1, this is 1, 1, this is 0, 0, and now what I will do is I will break this up into different elements. So, I break it up into 4 triangles, or I can remove this and I can break it up into 2 triangles and a rectangle, or I can make number larger, but for this description or this coverage we will just break it up into 4 triangles. So, this is element 1, element 2, element 3, element 4, and I will write down my global node numbers. So, global nodes are indicated in green, 1, 2, 3. So, these are global node numbers. Oh, actually I have in my nodes as 4. This is node 3, node 5, and this is node 6. So, this is important as we are formulating, we should very clearly identify global nodes and local nodes. And then the local nodes are 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Let us also write down the boundary conditions. So, what is the boundary condition on the right edge of the problem? U is equal to 0, right. What is the boundary condition on the bottom edge of the problem? Del u over del n is equal to 0. In this case the normal direction is y. So, I can also write it as del u over del y equals 0, okay, which means that the flux or the gradient of u, which in this case could be temperature, is 0. Then what is the boundary condition on the edge 1, 6? It is still del u over del n equals 0, which means that the gradient of u in this direction normal to the edge is 0. That is the thing. What is del u over del n? We had written it, del u over del x times nx plus del u over del y times ny. This is equal to qn, and this is also in our case it happens to be del u over del n, okay. So, del u over del n is 0 in this case. Very quickly we will develop the connectivity matrix for this. So, the B vector is how many rows? Number of rows corresponds to number of elements. So, it will have 4 rows. And how many columns? 3 columns, because the maximum number of elements in any maximum number of nodes in any column is 3. So, the first row, so this is row 1, row 2, row 1 is for element 1, row 3 is for 2 and row 4. So, row numbers correspond to elements. So, the entries in the first row will be 1, 2, 3. Entries in the second element will be 5, 2 and 3. Entries in the third row will be 2, 4 and 5. And entries in the fourth row will be 3, 5 and 6. Okay. For each element we will have an equation Ke UE equals FE plus QE. How many equations we will have for each element? 3, because each element has 3 nodes. If there was a rectangle, then that for that particular element we will have 4 equations. Here we will have 3 equations. So these are 3 equations. Total number of equations at element level, how many? Total number of equations, it will be 3 times 4, 12 equations, right? These 12 equations will be condensed, 12 equations at element level, they get condensed at assembly level. How many equations we get? To 6, because we have total of 6 nodes in the global domain. Further, once we apply the boundary conditions on primary variables, these 6 assembly equations, they get condensed to how many equations after BCs are applied? To 3. Why? Because U4 is equal to U5 is equal to U6 is equal to 0. So these 3 degrees of freedom, because they get eliminated, so we are left with only 3 equations. So we will just quickly write down those 3 equations. So what are the degrees of freedom left? 4, 5, 6 are gone because of the condition U is equal to 0. So the only degrees of freedom left are 1, 2, 3. And we will have F1, F2, F3 plus a Q vector. Okay. Now let us look at the Q vector. At node 1, how many components we will get in the Q vector? Only 1, and so I will get Q1 1. At node 2, at node 2, how many components do I get? I get 3 components. So I get component from 1, component from second element, component from third element, and the nodes are 2, 3, 1. Agreed? And at node 3, how many components do I get? I get again 3 components from element 1 plus from element 2 plus from element 4, and the nodes are 3 to 1. Okay. Now what is the value of Q1 1? Q1 1 is, again, actually I should have labeled these as capital Q's. We know that Qi for the eth element is what? Qn W ds integrated over the domain. Integrated over the domain. So, Q11 is the value of Q1 of Qn. What is the value of Qn at node 1? It is 0 because del u over del n is 0 at, right. So, this is 0 because of BC. So, we have to know what about Q21? They are all 0 individually because of the boundary condition. Same thing is true in this case. So, because everything comes to 0, we do not worry about this and we solve these equations. We solve these equations and we get our solutions. Okay. So, what we have seen in this class and also in the last class is that we can exploit this problem of symmetry or the feature of symmetry to reduce the number of, to reduce the complexity of the problem, and using that we can reduce the size of the problem and make our computation faster. So, whenever you encounter a problem which is symmetric in nature, and by symmetry I imply 4 things. The geometry should be symmetric about our reference frame. So, if in your FEA code the reference frame is not located at the point of symmetry, you have to shift your reference frame to the point of symmetry, only then you can apply the condition of symmetry. So, about the point of plane of symmetry, if geometry is symmetric, material properties are symmetric, boundary conditions are symmetric, and the forcing term is symmetric, then you can use that feature to reduce the size of your problem. So, that concludes our discussion for today, and tomorrow we will start a new topic which is related to numerical integration. So, thank you very much and have a great day. Bye.